right? So this is a picture, I think it's the Whirlpool galaxy. This is one of the ones you can see with a telescope. You need a telescope to see it, but just about any telescope you might buy, you could find this thing. I think it's below the Big Dipper. And some students in New York wanted to do a presentation on galaxies. They were supposed to do galaxies, so everybody takes a picture of the Whirlpool galaxy because it's so pretty, right? And so you guys can do this too. There's an observatory at Pine Mountain, and there's, by the way, there's all over the country. There's not huge telescopes, but pretty big telescopes. You know, there's 30-inch telescope. There's a 50-inch, 60-inch telescopes, right? Pine Mountain has a very, very nice telescope, and they've got a web page, and you can say, gee, I would like a picture of this, and they've got a person there that will take a picture of that, and now I believe using the power of the internet, they can send you an image of that, right? So these kids said, gee, take a picture of this because we just need it for our presentation, right? Never mind that there probably are many pictures, right, of this galaxy, right? So they take a picture of it and send it to these kids, and it turns out a few days later somebody notices a supernova. That star wasn't there before, right? And that star is, by the way, as bright as the entire galaxy, right? So one star for a few days can outshine the entire galaxy, right? And what's interesting is that when these supernovas are just beginning, it's crucial to look at them because we can tell kind of by the beginning, the way they begin, what type of supernova it is. And if it's a particular type, it's a very interesting type because they're all about the same brightness. And so we use those as sort of these standard candles, right? So everybody said, gee, there's a supernova going on at this galaxy. It probably started about 3 or 4 days ago. Did anybody happen to take a picture of that galaxy? Well, nobody had except for those kids, right? They just happened to take a picture, right? So they, unwittingly contributed to science. Yes?
So how long do they take to like
in the space of a few days. This is a collapse that happens in a few days. So it's dramatically rapid for a star, right?
Teacher better giving them extra credit for that piece of paper.
I hope they did, yeah. I know, it's like, that's kind of funny. Okay, so if you have a supernova, the remnant of a supernova has a compact remnant, okay? It's composed almost entirely of neutrons. A white dwarf is the size of a planet, so this thing before it collapsed was the size of a planet. A neutron star is the size of a town, yeah? So this is just an incredible thing. A teaspoon of neutron star material weighs more than 1 billion tons, right? So this is just incredibly dense stuff, right? It's like, so if you walk around a neutron star, be sure to shake all the dust out of your pants, I'm just joking, right? Because they represent such an incredible collapse, almost all stars spin, right? I'm saying almost because they probably all do, right? Okay. But neutron stars, some of them spin thousands of times a second. This is just an amazing rate of spin, right? And in the core of this thing, you cannot have atomic nuclei. There's so much pressure that it's just the superfluid, basically, of neutrons. In fact, I think Timothy Ferris said that it's some small thing, like the width of a hair would be Mount Everest on the surface of a neutron star. It's a perfect sphere. It's absolutely perfectly spherical. And then there's an outer envelope, maybe a mile thick, just a crust of sort of nuclei and electrons that didn't get in on the party, right? Stuff that's just sort of on the outside of it, right? Layer of rust or something like that. Okay. And then the core is actually a superfluid, right? Superfluids are things that, although it's so dense, right? Superfluids have no fluid friction and stuff like that, right? It's a crazy. Well, now that is just such a good question. The question was, how do you observe a neutron star? And then the problem is, of course, they don't emit light. Okay, but they do emit some kind of radiation, right? Okay, so in 1967, I'm going to answer this question. It's a long answer, right? So in 1967, Anthony Hewish of Cambridge University, he's studying. Basically, he's trying to eliminate the solar wind when it hits the Earth's atmosphere. Causes the radio telescopes to have this sort of a interference called scintillation, right? Okay, and so what you do is he's trying to basically look at this defect in radio telescopes, right? And so guess who gets to stay up all night? The guy with the PhD or the graduate student? Yeah, the graduate student. Would you please stay up all night and do this like routine check of the radio telescope, right? And so I believe it entailed just pointing the telescope in different places in the sky, not for any particular reason, but just to see, you know, relative to the solar wind impinging on the atmosphere of the Earth, you know, what is the radio interference at these spots, right? Okay. She points it to some place in the sky, and she starts hearing bip 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 bip. Now, obviously, what has she found, right? Nothing out there acts like a little clock. There's nothing in the sky that could ever make a sound like bip 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 bip. Just boom 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 boom. Right? Obviously, she's unwittingly pointed it at a satellite or a hill or something. I guess in 1967 were that many satellites? Probably not so much. Right? She's pointed, but there's some like the wind is blowing a wire and it's bumping up against the observatory. There's some motor that's got a bad. There's some. It can't be out there, can it? Yeah. Right. So she's doing everything. She's trying to figure out where's this noise coming from, right? You know. And then it's like it turns out that this thing, if you all stars move across the sky, yes, right. So how many people have looked through a telescope and seen when you zoom way in on something that it sits there and moves across the field? Have you seen that? Yeah, they move like that. So if you spend a little more on your telescope, there's little sidereal tracking motors. Those things sit there and track the sky. Just a clock, right? But it's not a 24-hour clock. It's a 23-hour, 56-minute, 4-second clock, right? It's sidereal rate. It runs like that, right? And so she discovers that when she turns off the tracking on the telescope, this thing drifts out of range, and she quits hearing it, right? But when she goes back to that location with respect to the stars and turns on the tracking, it stays right there, right? So it's definitely out there. It's not here, yeah? After checking everything else, I'm sure, right? Here is a little picture of it, right? This is about, these things here are about 5 seconds apart, right? So this one's going about once a second, yeah? A little faster maybe, right? So this is called a pulsar, right? How many people went and checked this thing?
I did. All the questions.
All right, good for you. Okay, I want everybody to do that. So go through this thing and answer all these questions. I probably will collect this because that's the only way that you'll do it. But that's one of the possible outcomes, right? Is that if it, you know, it says if there's the object spinning and we can see flashes of radiation down there, what is the object called? It's called a pulsar, baby, which is, by the way, a car made by Nissan, or used to be made by Nissan. I don't know how they get, what? Nissan. Actually, here's a funny thing. Do you know that Mazda is actually pronounced Matsuda? Matsuda. Makes sense, right? Because there's no, in Japanese, there's not Mazda. There's no like consonant sound, right? Matsuda. Yeah? It's crazy. I don't know how Nissan is pronounced. Probably Nissan. But anyway, this is a pulsar, right? And then this is just crazy, right? Some of the pulses are like a 40th of a second in duration. And so if you think about that, if you look at a star, you know, here's this star, and the width of a star, you know, how wide is our own star? What's the width of our own star? I don't know. We can look it up. Let's look it up. Okay. So the radius of Earth is unavailable to us because it's under the document camera. Like, where'd my textbook go? That's the other place that I never look. Okay. So our star, our own sun, and our sun is a pretty averagey sort of thing, right? The sun has a radius of 6.96 times 10 to the 5th kilometers. So it's 6.96 times 10 to the 8th meters. Now, if our star were blinking on and off, like some sort of like flashlight, right, turning on and off and on and off, right, okay, we would see the light from half of this star. So we'd see light from about 3.5 times 10 to the 8th meters, yes? Now, when it turned off, let's say the whole star turns off, the light from here, we'd stop seeing this first, and we'd stop seeing that last.